All right, folks, today I'm going to tell you how a VOR works. Now, I'm not going to tell you how to navigate using a VOR, how to proceed direct to a station. I'm not going to tell you about to and from flags, etc. I'm going to tell you about the VOR itself. VORs, as you well know, by the way, let's talk about this real quick so that if I use the terms, you know I'm really kind of using them synonymously. A VOR looks like an upside down ice cream cone. It's white, and that's pretty much what it looks like. And there's antennas around the thing, and sometimes it sits on a platform if there's undulating or varying terrain around there. This is a VOR, and if there's a DME station, radio co-located with it, then we call it a VOR DME, and I'm not going to talk about the symbology. But if there's a co-located TACAN, tactical air navigation, with that VOR, then we call it a VOR TAC. And the VOR part is still the upside down ice cream cone, and the TACAN part is a white cylinder typically that sits on top of the VOR. And there are some places out there, especially military airfields, where they'll just have a TACAN sitting on a little tower out here by itself with a little guy wires holding it up. And of course, it still looks like the little white cylinder. So you can have a VOR-TAC, a VOR, VOR DME, or a TACAN by itself, standalone. So if I say VOR-TAC or VOR, I'm obviously talking about the VOR portion of that, but I will touch on TACANs here in just at the very end, just to tell you what TACANs do related to VORs. But we're going to talk about VORs and what they do. Well, they transmit a radio signal, and it's a baseline signal, and it's at a frequency that you can dial up yourself. So, for example, 112.50 is the frequency for the Black Forest VOR DME, and that's for the VOR portion of it. And of course, if I wanted to dial in the DME, I'd put in a specific channel number, and I don't use it, so I don't remember what it is, but I do use the VOR every now and then. And this is the frequency of that VOR, 112.5. I'm going to write it up in the corner here, 112.5. Now, if you remember from trigonometry, or if you've got some advanced engineering or mathematical education, you'll know that a waveform or a radio wave can be represented in a waveform that looks something like this. A sinusoidal waveform. And sinusoidal meaning that the thing scribes out a sine wave. And I'm going to take out this part of it, just like so. And it repeats itself. And the number of crests or high points that pass a given point, or that occur or are transmitted or receive every second, is that wave, that wave's frequency at 112.5 kilohertz. And there you go, that's the Black Forest VOR waveform. Now, inside the VOR, if we were to look down on the thing, looking straight down, and of course it'd be an ice cream cone, upside down ice cream cone pointing up at us, there's a part inside here. It's a transmitter, and the thing rotates inside the upside down ice cream cone 1,800 times per minute. RPM, let me get that right. And if you do the math, you can figure out how many times per second. But this transmitter inside here rotates. And I'm going to draw part of the interior here, and here's this transmitter thing that rotates. Every degree that it passes through, it transmits a signal, a separate signal that is modulated or phase shifted. I'm going to write it here because you can look it down, look it up yourself. It's phase shifted. And how much is it? By the way, when we phase shift a radio wave, it just looks something like this. If we take this radio wave and just phase shift it to the right, it would look something like this. That is a phase shifted radio wave. In fact, it's been phase shifted 90 degrees. And I'm not going to go into trig here, but this could be represented as the 0 degree point. This is 360, this is 180, this is 90, and this is 270 along this sinusoidal waveform. And I'm not going to get into it. You can go Google it and look it up when we talk about phase shifting. So this antenna, as it's swinging inside here, as it's spinning inside here, when it passes 1 degree, and I mean, obviously, it just barely turned 1 degree from magnetic north. It transmits in all directions, by the way, omnidirectional. That's the O part in a VOR. It transmits a separate signal that is phase shifted by 1 degree. And I'm not going to do the math here, but I am going to put 112.5 plus 1 degree of phase shift, whatever that frequency is. The frequency actually would be the same, but we're phase shifting the baseline frequency. And of course, that would be transmitted in that direction. And suppose it swings through 30 degrees. Now it's going to transmit a signal in that direction, technically in all directions, that's phase shifted 30 degrees. So then we'd have 112.5 plus a 30 degree phase shift. So its waveform would look different. So again, we have the baseline signal going out at 112.5 in all directions. And then there is also a phase shifted signal going out, very accurate by the way, along every radial, 360 degree radials. And the frequency for each of those individual radios is equal to the baseline plus however much the phase shift is. And there you have it. What's cool about video, you can hit pause, draw this, look at it, study it. That means I can erase it. So let's draw this again, kind of from the 30,000 foot view. Here we are. Here's our VOR DME, and I'm going to try my best to draw what it would look like on a map. In all directions, there's a baseline frequency of 112.5 going out. And along every radial, there's the baseline plus the phase shifted amount. So let's use 030 as an example. So shooting out at 030 is 112.5 plus, or added to an additional frequency that's 112 phase shifted 30 degrees. So here's 112.5. Now there's a second one that goes out that's phase shifted 30 degrees. So if that's 90, there you go, about a third of 90 phase shifted. And that's pretty much it. And now what is cool is that your navigation instruments inside your aircraft, your nav radio, etc., your OBS, remember the OBS is not only just the little knob down here, but the whole instrument itself is called a OBS. We could call it a nav instrument or VOR. You can call it whatever you want to. But what this thing can detect is the radial we're on, not because it knows where we're at in relation to this thing. It simply is getting a baseline signal and then another signal phase shifted by that amount. It's getting it all. And so when we center up the CDI with a to or from, it doesn't matter. When we center that up, so let's say there's a number of radials going out here, and we happen to be right here, and again, the direction that we're flying does not matter to this thing. When we center up the CDI, we've told the VOR, in a sense, show me where I'm at in relation to the radial that I'm picking up coming off of here. Excuse me. And of course, the CDI centers. If we're on the 030, in fact, I should do that in the cyan color like I did earlier. If we're on the 030, then this will center up when I dial in 030. Or, of course, 210 if I wanted to dial in the reciprocal, and then, of course, I'd get the to from flags. That's a whole separate discussion. But what's cool is my navigation radios, by virtue of centering up the CDI, can tell me exactly which phase shifted signal I'm sitting on. And of course that corresponds to a specific radio. If I continue, if for example in this drawing I'm pointing southwest, if I continue to fly southwest and do nothing with my OBS knob, then my CDI will start to swing. Why? Because I am no longer on that radial or that phase shifted signal. Now I'm on the 035 or whichever one I happen to be on. So bottom line, that's how your VOR works. It sends out a baseline frequency, an example of Black Forest, 112.5, and then for every radial, and there's 360 of them, shooting out. By the way, how much phase shift do you think there is for the 360 radial? And of course, these are oriented to magnetic north. Zero phase shift because I'm on the 0 degree or 360 radial. Either they're one and the same. So for every 1 degree, I transmit another signal that's phase shifted by 1 degree. And my radio can pick that up and tell me, therefore, where I'm at relative to the VOR. As promised, I was going to talk real quick about TACANs. That's the cylindrical device, developed by the Navy, by the way. I guess they tried to use VORs to fly to ships, and because of the rolling movement of the deck of the ship, the VOR signal didn't work right, and the spinning mechanism maybe didn't work right. I don't know. I've tried to find the technical reasons why VOR didn't work on rolling decks of carriers, but so the Navy invented the TACAN, TACAN, Tactical Air Navigation. And they invented the TACAN, and it spins also inside here, but the way it does so, I guess it's gyro stabilized, so we're not shooting, radials down into waves. I don't know, honestly, but it was developed by the Navy, and it works the same way. There's a device in there that spins around, and it sends out 360-degree radials at certain frequencies, and we don't dial those frequencies into our airplane. We simply dial in a channel number, and our radio tunes in the appropriate frequency for us. So it works identical to a VOR. One subtle difference, as you probably know, a VOR has a cone of confusion. Right when I'm over it, and the width of that can vary, but when I'm over it, the CDI is all over the place, and I really can't use it for navigation. At the moment, I have to just press out of the cone of confusion. One thing that's interesting about the TACAN, its cone of confusion is just out of control. It is very, very, very large and very wide. And because of that, if you're ever told to hold over a TACAN, you got to say, nope, can't do it. Because the cone of confusion is so big, you'd be 5 miles past the thing probably before you'd start your turn, and you'd be late. You can hold over a VOR, and you can hold over a VORTAC, but you're using the VOR portion of it. But if you are TACAN capable, and for whatever reason why you would be, I don't know. If you are TACAN capable and using the TACAN to navigate, I'm not talking about the DME part of the TACAN. I'm talking about the radials. You can't do it because the cone of confusion is too big. There you have it, folks. That is how a VOR works. If you like this video, if it was helpful, go to my website, and I talk about a lot of these concepts. 777 aviation.com. I sell instrument pilot and private pilot study flashcards, and I've put about 30 years of flying, to include instrument flying, into those cards. And I guarantee that you will pass your oral exam and be a better instrument and or private pilot. So go to that website, check out the testimonials, and as always, if there was a mistake, you've got something to add to this, it can make it better, let me know. If you liked it, subscribe. And always, I appreciate the comments, and I interact often as much as possible with folks that watch here and make comments. So thank you very much. Hope you enjoy it. See you later.